All right, good afternoon, everyone. Any questions? Yes. Quiz question 9. All right. Is that this one here? Oh, the 4 queens. Okay, hold that thought. I'll come to that very question in a minute. Other questions? Yes. Yes, so I'm going to increase the timing of that. Someone sent me a perfectly good solution, but you could send me privately your solution as well, and I could have a look at it. It's a little hard for me to tell whether it's an infinite recursion, which would time out, or whether it's a correct solution. But someone had sent me something that sometimes times out, so that would be an error on my side. So for now, I've doubled the timeout. We'll see if that takes care of it. But if the problem recurs, privately send me your solution. I'll have a look at it. It could be that CodeCheck is getting busy, and then I'll have to worry about it. Maybe everyone else is throwing at it infinite recursions, and that's why yours gets raised slowly. Other questions? Yes.
So I was doing 5C final, and then when I put the CodeCheck just to see what I got, it took around 2 minutes before my results appeared. Is that what's supposed to happen?
Well, like I said, it may be that CodeCheck is right now bogged down. I'll have a look at it tonight and see what it does. I mean, it's some set of servers in the cloud at Google, and maybe I need to reset them or something. I don't know. Yeah. 5B final? Yeah, let me look at it. Yes, I'm sure I can. Oh, yeah. So, before doing that, let me back up just a little bit. So someone else asked me earlier today with this polygon thing. So here I have my polygon, and said what to do in the final version. And so I said, well, the deal was we would cut off this triangle. And then he said, oh, I know, then I'm just going to loop over the other triangles and do it again. And I said, no, that's not the point at all of this question. So we want to do this recursively. So recursively, we're going to be constructing what? So we're having this big polygon here, the one with 6 corners. Let's give it a name. It's Fred. And so we're asking Fred, what's your area? and Fred thinks about it, cuts off, probably doesn't cut off, but just measures this area here, and then how is Fred going to figure out what's the area of the white part? So the key here is that what Fred is supposed to do is to make a new polygon How do you add points to polygon? Does p dot add? Can someone confirm or deny? Does p dot add? Yes? And does it get area? And then it's going to say to his buddy P, hey, how big are you? Right, this one here is P. And then Fred is going to take whatever the, P said and add the yellow area and said, that's how big I am. Yes?
I was wondering, what's the easiest way to, because I couldn't figure out how to figure out which point to get rid of for the new polygon.
I see. All right.
If I had the wrong one, then
So let's just name these corner 0, corner 1, corner 2, corner 3, corner 4, and corner 5. Just always cut off the ones with corners 0, 1, and 2.
just cut the one in the middle. That makes sense.
And then which ones do we need to add for P? So we need to add C0. Right, that's the one over here. We need to add C2. We're skipping C1 because it was cut off. We're adding on C3. And we go to what? C. Well, we need C5 still, right? And in general, we go to Cn minus 1, right? And so, of course, once you for pseudocode, you would want to actually write this as a loop, right? Because in pseudocode, you can't have dots. Dots are good for first creativity, but in pseudocode, you would want to have a loop. I've pretty much written the pseudocode for this one now, or indicated how you can write it. Yes?
So, do you have to do power polygon? You just remove one of the points from the corner in the grader.
Yeah, you don't have to do it, but if you don't do it, I will make sure that the grader takes off some points. I want you to do it just this way. And CodeCheck can't necessarily enforce that. So the reason I want you to do it this way is because I think, and maybe I'm the only one, but I think it's a nice way of visualizing how to do recursion. The recursion means make a simpler problem, solve the simpler problem. And here we're physically almost making that simpler problem. We're making that other polygon. So I want you to make that polygon. I really want you to do it. Okay, and I will tell the grader to take points off if he or she finds that you do it in any other way. Of course, there are many ways of computing the area of a polygon, and there's some closed formula somewhere. Or like what the other person was trying to do is just chop it off into a whole bunch of triangles. And I don't want any of those. I want this particular approach, make the smaller polygons, because I want you to feel yourself how to make a simpler problem, how to solve that simpler problem. Because I think it's super elegant, right? You're asking this big old polygon how big it is, and it just looks at one corner of itself, says, oh, this area is that big, makes another polygon, and without worrying how that other polygon is going to do its work, it can then say with confidence, my area is the sum of those two. So, having said that, I thought one can do the same thing with the demolition. So, what we want to be able to do is give a result that shows how the cheapest demolition actually works, right? So we want to be able to say what gets split off, and over here we see that the A gets split off, then here the R gets split off, the E, and so on. So this shows like the history of this this demolition. And at first I said, well, of course, what one could do is one could make it so that over here, the cost function, that instead of returning an integer, we would return a string, or would somehow build up the string. And when I tried to do that, I found that actually surprisingly difficult. I'm sure it's possible, but then I said, really, let's just work it in the same vein as with the polygon, that we say a demolition is an object. And so this object knows the whole story of the demolition. And so what does it know? It knows how to split off the first characters, or the last, right? So it knows the choice of the first or the last, and it knows then the story of what happens with the rest. So a demolition object here remembers the story on how the rest gets demolished. And now what you want to do is, when you construct a demolition object, the constructor will do all the work. So it says if the string is of length 1, then we'll just set the description and say that's the end of it. And the cost is 0, and the cost is already 0 by the default construction here. Otherwise, now you have two options, right? You either take it off the front or you have to take it off the back. You compute the costs of both, and that tells you which demolition you're actually going to be carrying out. And you just throw the other one away. So the one that you keep, you attach to this rest demolition. That way you're going to be keeping the history of one or the other rests, and you also want to update the story, the description. And so what do you want to remember in the description? You want to know what it is that you took off. That's really all you need to set it to. Are we calling toString or getDescription in the end? No, we're just printing it. So this thing here calls toString. And so if in the description you put on, in this case you would put either R or you put A in the description. And then you call toString, and toString will then return the description, that's the A or the R, and then it'll put in the rest. And then you'll get one of these strings. Alright, so here, but now I don't, oh, I see. So I'm all wrong. The description here, the description is A space member, or it is AM, so it's one of the following two strings. It's A space member, or it's AMB space R. So that's the description. You set it to one or the other. And then you see over here the arrow. That's what comes out of this part. Here's the arrow, and here is the rest demolition. Yes?
Another question. For the polygon part, for the polygon assignment, what I did was that I computed the area. I used recursion to find the area of the other triangles, but then I removed the point from.
Oh, don't do that. I see. That is a tempting thing to remove a point from the polygon, but that's a nasty way of doing it. I mean, that's like saying, if I ask you how tall you are, and you first chop off your head, and then you ask the rest of you how tall is the leftover, right? So you generally don't want to mutate things, and in this particular instance, I don't think I have a test case for that, but I really want you to construct a new object. Leave the current one unchanged. You never want to unnecessarily mutate anything. So when you remove something from a list, you should always ask yourself, is this a good idea to now change that list? Because when you ask a getter method like get area, you do not expect that polygon to shrink itself down to 0 or to a triangle when it's all said and done.
But then in the beginning, for the else loop in the recursion, I got 3 points, and I computed the area, and after that, I removed the point. And it just keeps on doing that until it reaches my base case. And then when I tested it, it was right.
Well, when you tested it, what did you test?
When I went to the code check,
Well, but that doesn't tell you much at all, right? That says that code check, which only asked for the area, what I should put in the code check test, and I might if I have the time, is it check whether the polygon was still intact afterwards.
okay.
Because a method like get area is not supposed to break down the thing that you call it on. And an easy way that I could test that is I could call it twice. I should make a note for myself. So if you call and then you call it again, you of course expect the same answer. But if you destroy it in the process, then that would not work. So definitely don't do that. Yes.
Once you break off about, you said that we need the remaining string to the demolition.
You make it so in here, you're going to have to at some point make a new demolition. In fact, you have to do that twice because there are 2 demolitions that you want to study. You want to study the demolition of the first rest and of the front rest and the back rest, so to speak. So you make yourself those 2 demolition objects, and then once you have those 2 demolition objects, call them Fred and Wilma. You say, Fred, what's your cost? Wilma, what's your cost? You pick the cheaper one. You remember it. You just link it up to that rest demolition, and you throw the other one away. I mean, you just ignore the other one. You don't do anything with it. So again, if you think about it as an object, a demolition is something that knows how to demolish the string. Then you say, I need to demolish this big string. Let me find out how to demolish these smaller pieces by just making another object of that kind. So a demolition is something that can tell you a story. It can tell you what's the cost and how did it look like. Yes?
So in the code that gives you the get area method doesn't have any parameters, but we should change that so that we can call it on a new.
No. You make a new polygon. Over here you see this. So you make a new polygon, P, and then you call get area on it. Okay? And you see that's the genius of doing it with objects, because you now have a new object and you can call it on that. When you see the kind of more traditional recursion where a function calls itself, that I always find that's more mysterious, because the function calls itself and calls itself. Here it calls that function on a brand new object. And so to me it's completely plausible that this must succeed. We have a new polygon and you just ask it, what's your area? Yes, so in both of these cases, what I have in mind is that you make this this new object and then you ask the object the recursive question. I agree with the polygon, it's concrete, and with the demolition, it's kind of more abstract. Yes?
So one question, let's say for Android, you have 2 console stuff, does it matter which one you're using?
Not to me, but when you report it, you have to break the ties so that there's a unique solution. And that says, in the final, break ties towards choosing the first letter. So if both of them have the same cost, then prefer the one that uses the first letter. And that's only there so that the grading is unique. Because otherwise, a poor code check would have to figure out what to do. Code check can't do that. It can only check whether the outputs are the same. It can't reason about the thing. So that's why the tie resolver is there. Other questions? All right, then I had a question about the puzzle. Where's the puzzle? Let's see. All right, so with the puzzle in the draft, there was no recursion at all, right? So all we're supposed to do in the draft is do what? How many methods? 1, 2, 3, 4 methods. And so let's do the easiest method first. So how do we do contains? We want to know whether that digit is anywhere at all in what, add 1, add 2, and result, right? Well, that seems like pretty easy. Okay, so I would just concatenate the three strings because we just want to know, is it in there? And then I use the string method contains. So if you've never seen this method, this would be a good chance to become acquainted with it because it is super useful. So is solved is a little harder, so I'm going to skip that for now. First letter. So now I'm supposed to find the first thing that is a letter in this puzzle. That's a standard loop, right? So again, I might as well go through the concatenation. Am I? Oh, I want to be in level 1. And it's not add 3, it's the result. So over here it's not the result. So when you traverse a string in Java, you have two choices. You can look at substrings of length 1, or you can look at the characters. Which one do I want in this case? I want characters. Why? There's a classifier, character.isLetter. Those classifiers unfortunately only work with characters and not with strings. So it is char C equals, what is it? All char I, and if character is letter of C, return. But now I do need to return a string, so I need to change it into a string. Just concatenate with the empty string. And otherwise I return the empty string. Okay, is solved. So I need to know that thing has no letters. So if there is a letter, then first letter would return it to me. In this case, I can return false, right? If add 1 starts with a 0, then I can return false. So the same thing for add 2 and result. And so in this way I chip away at the problem, one of these things at a time. Notice the nifty starts with function, it's often useful. And now I finally know that they're all numbers. So So now I need to add them together and check the answer. So what I'd like to do is to say return what's integer parse int of add 1 plus integer parse int add 2 equals integer parse int of result. Well, that should work, right? Because if there's no letters, then the parse int should succeed. The other way that you can do it is, instead of making this test here, you could just try to do the addition, the integer parse int and the addition, and if it throws an exception, then you catch that and you return false. But maybe that's harder. The other thing that I wanted to say is there were a number of people on Piazza who seemed to be unfamiliar with the fact that you can return something in the middle of a loop or in the middle of a function. And that is really a very useful thing to be able to do. So there were some people who kind of looked at the first character and they said, oh, it's a letter, and then their pseudocode kept on going through the entire rest of the string. And there's no reason for that. As soon as you know the answer, you can bail, you can return. There are programming languages where that's not the case, but in Java, that's fine. Yes?
Can you show briefly how you would catch an exception and return false there?
Sure. So if in this case, I wouldn't need this test. I would just put a try block here. And pardon my formatting here. This is not an IDE. What exception gets thrown? Like a number format exception? I like this. Yeah, that's fine too. And finally, we have this thing where we need to construct a new puzzle by replacing a letter with a digit. So we return a new puzzle of add 1 dot replace letter add 2 dot replace and then result dot replace. That's it, right? So what I wanted to point out that in the draft part of this here, this required nothing but basic stuff from 46A. All you had to know is how to convert strings to numbers, convert numbers to strings, test for starts with, test for contains, write basic loops. And so this really is the kind of stuff that that you're expected to do in about the same speed that I've done it here, maybe a little bit faster because you're sitting in front of an IDE and don't just type it into a text area. And so if that's not the case, you really need to practice your 46A coding muscle, that you can crank out these kind of things without thinking very hard about them. So a basic loop that loops through an array of characters, if that sets you back into research for 3 hours, that really is a problem. That's like when you're trying to learn, let's say, French, and in your second year of French, you still have to think how to say I and you. So you really do have to do those things. If you find that that's your problem, that's what slows you down, my strong recommendation is that you practice more of these really basic loops. And I will put up a couple of sites where you can go to do that kind of practice. But that would seem to be an essential thing to do. Because if you can't do that, it's just like speaking French without being able to say I and you and how and where and that kind of things. So basic looping, basic string extraction, converting between strings, characters, numbers, that at this point really should be standard stuff. All right, so that's this one here. Once you have that, then you get to enjoy the recursion. The recursion, as it turns out, is not actually that hard if you follow the recipe. Okay, so that's what I wanted to say about the homeworks, and I hope that that'll help you progress with them nicely. So in today's lecture, it goes through a couple of complex examples for recursion. And so, like I said, the basic recursion where you just compute the sum of the numbers from 1 to n or some such thing, those are pretty easy, but they're also not all that exciting or useful because you could do those with simple loops. And so the power of recursion comes in when a simple loop no longer suffices. So for example, with the string demolition, the reason that the loops don't suffice is that what you're really doing is you're climbing down a tree. That each time there's two decisions. You either break in the front or you break in the back. And then this decision has two more decisions, and this decision has two more decisions, and so on. And so that's something that is hard to do with a loop. But recursion is okay because you only worry about one level at a time. One of the worked examples that I'm not going to go through right now, but I hope you've glanced at it, the worked example with traversing a directory tree is the same thing. You have a directory, you have subdirectories, you have sub-subdirectories. If you wanted to traverse them all, then to do that with a loop is essentially, well, it's possible, but it's very difficult. But with recursion, it's pretty easy. You just worry about one level at a time. We're going to be seeing many more of these in the later part of the course. This example here is kind of complex, but it's a well-known example, and you should have seen it at least once in your life. And it's a set of recursions that call each other. So the problem that we want to do is we want to compute arithmetic expressions such as this one. Now, of course, you know how to do this because you've had many years of algebra. But when you first learn it, it is not so trivial, actually. I have 8-year-old daughters who are right now learning this, and they find it surprisingly challenging and don't even see the point of the parentheses quite yet. So you need the parentheses, of course, because by tradition, the multiplication binds stronger than addition. And so you need to sometimes change the order. So how do you evaluate something like this? And there's a standard algorithm that does this, and it parses them using these nifty syntax diagrams. So if we have an expression, for example, 3 plus 4 times 5, then we say, all right, so we want to first find a term, and then a plus or minus, and another term. And so this will turn out to be a term, and this one also will turn out to be a term. And then when you have a term, then it might be just a single factor, that's the case here, or it might be a product of two factors. So over here you have a factor and another factor. And when you have a factor, it can do one of two things. It could be a number, all of these are numbers, or it could be another expression. For example, you could have 3 plus 4 minus 5 times 6, or some such thing. And so you break it down according to these linguistic rules, so to speak. And for evaluation, you can simply follow this order. So, and I don't want to go into these details here. I just want to go into the implementation. So for the implementation, what we do is we write three functions. We write a function for each of these syntactical elements. The get expression value will compute the value as an expression, and that's the most general. Get term value will compute the value assuming that this is a term. It'll only work for the next term. And get factor value for the next factor. So again, what's a factor? A factor is either a number or a parenthesized expression. So, okay, well, let's have a clicker question. Why not? Been talking for too long? No, how's my... All right, so let's see. So, so the question was, why do we need both terms and factors? So why are we having all of this rigmarole that we have this category of terms, this category of factors, and so the first one says factors are combined by multiplicative operator. Is that correct? Let's find out. So that is correct. So factors are combined by a times and slash, and expressions are, and terms have a plus and minus. So one is a correct statement, but is it a reason why we need terms and factors? I mean, it's a statement, but I don't think it particularly explains it. 2 is plainly wrong. So 17 people chose it anyway. And 3 is that really is the right answer, because if you have an expression such as 3 plus 4 times 5, you need some way, when the computer reads this thing, I mean, the computer can't just do what we humans do, right? We intuitively glom onto the star and say, oh, that's stronger. But that doesn't really work if you have a long expression. You know, this is still something we have been staring at equations for so long that we see these parentheses, and we know right away this thing here is the computation that we need to do first. But that's not how a computer thinks. A computer has to somehow process this thing from left to right, and then figure out, should it execute the plus or should it look further? And so that's where this looking further is complicated by the fact that we need to look for stars, and that's what the terms and factors do. It gives us a way of differentiating our activity. Should we compute right away or should we look further? So that's what we need. And do we need both, that we can have mutual recursion? Not at all, because there's no mutual recursion because terms and factors. The mutual recursion comes in when, let's close this poll. The mutual recursion comes in when expression calls term, and term calls factor, and factor calls expression again. That's the mutual recursion. So if you have a parenthesized expression, then you get a recursive call. So the only recursion is because of the parentheses. If we had no parentheses, we wouldn't need recursion. So I'm going to go through one of these methods very briefly so that you see how this works. So here's get expression value. And so here it calls get term value. So let's just try this out with like 3 plus 4 times 5. And so get term value is going to read off the 3, and then somehow magically it's going to stop. It's not going to read the plus. And then it's going to return the value of the 3. And we'll think about in a minute why that is. Then we read the next token, that's the one over here. So we're now here. And it's a plus or a minus. And now we're here, we're discarding the token, so that's out of the way. And then we call get term value again. And now magically, get term value will deliver us the value of this term, and it'll say this thing is 20. So the first one, this value was 3, the next value is 20, and then it's going to add it up and update value here to 23. And it's going to return it and say it's 23. Why is there a while? Because there might be another plus in here. There might be another plus 6 or here, and they'll all be read off one at a time. So the question really is, how can get term value magically stop at the right place? How can it stop before this plus or before that plus? Well, I wish we had it. I should have put it here. Okay, well, it says it's the same way. So I don't know why I didn't put it. So it is in fact the same way, and it stops at a star or a slash. So let's again look at 3 plus 4 times 5. So what it's going to do is it's going to read this number here, and then if the number was followed by a multiplication or division, it would keep on reading. It isn't, so it stops and returns the 3. This one over here, it's going to read the 4, and then it's going to grab the multiplication and the 5, and then compute the product. But if I had 3 times 4 plus 5, then the term would say, okay, this thing here is a factor, and then it would know that this whole other thing is another factor. And that happens over here, where when it sees an opening parenthesis, then it's going to throw away the opening parenthesis, and then it's going to call get expression value again, which recursively can read a whole expression. All right, so let's try this. And so I want you to trace these things by parsing this expression. So called get expression value on this input. And you can guess your way through. The next token thing either gives you a number or a plus or a parenthesis or whatever. And let's find out what happens. So start with get expression, read this thing through, and because it's a malformed expression, somewhere it's going to not work. So this parser that I've given you, to keep life simple, I've not put in any error handling. I know some of you don't like error handling. So parse it through and figure out where the expression gets through. That should take you a few minutes of looking through that code. Let me set up the question. Yeah, get out a sheet of paper and try this with your neighbor. And it's more fun. Three plus 4. All right, let's do this together for a minute here. So over here, we're starting with get term value. What's get term value going to get? Where is it going to stop? It's going to get the 3. Let's see why that is. So get term value is, where is it? Here. Get term value calls get factor value. Okay, here's get factor value. Get factor value looks for a parenthesis. Do we have a parenthesis? No. So otherwise, it gets the next token, which is the 3, and returns 3. That was get factor value. We now return to get term value, which returns 3, and we're back here at get expression value with 3. So now it gets the plus. So now we're reading off the plus. It's gone. We are now calling get term value. So let's see what's get term value going to do. Get term value calls get factor value. Get factor value doesn't see a parenthesis, so it's going to go inside here and return 4. So get factor out value returns 4 to get term value. So we're right now here with 4. So we go into this loop. We peek at the next token. The next token is an asterisk. So it's happy and says, I want asterisks. It reads it off. And it calls get factor value. So now get factor value is called. And it's going to look at the next token. What's the next token? It's this closing parenthesis, right? Oh, I should look at what my poll is doing. Okay. So the poll overwhelmingly favors choice 3. Let's remember that. So get factor value is going to look at the opening parenthesis, which this is not, and so it's going to rush right into here, and now it's going to convert the closing parenthesis into an integer, and that'll throw an exception. So let's see what the, wow, okay, so not too bad. So 2/3 of people seem to have understood what I thought was a pretty complex situation. All right, so that's all I want to say about this mutual recursion thing. It's a useful trick. You're going to see it again in your programming languages class, and it's just there. So now I want to talk about backtracking, and there's a good reason I want to talk about backtracking. Namely, this is actually what underlies the puzzle homework. Right? In the puzzle homework, you are trying something, namely to substitute the first letter for 0, 1 up to 9, and sometimes it works and you keep on trying, and sometimes it doesn't work and then you throw away what you have done. And so it's a very important and useful technique. So you build up a partial solution. What's a partial solution with a puzzle? Can I have a little less echo in the back? A partial solution in the puzzle might be x3a plus a20 equals whatever, c3b. Okay? Why is it a partial solution? Because we've already replaced some of the letters, but not all of them. That's pretty partial. And so now you look at it and you accept it if it's an actual solution. That would be the case if you ask what is the next letter or the first letter and you don't get any. Then you say then it's actually a total solution. And now you need to check whether it could continue being a solution. And so the way we're doing that is we're figuring out which are the digits that are not in there, and then we put them in there, and then we check, does it work? It doesn't work if the math is wrong, right? And it doesn't work if one of them starts with a 0. But if it still does work, we can extend it. So that's a very straightforward way of solving a problem. The complication when you do it by hand is to remember where you are. So when you do this, and you must have done that at some time in your life, like with the Rubik's Cube or something, right? It's easy enough to solve Rubik's Cube, right? You make all 6 possible twists, and then recursively you keep on going. But to keep it in your head, that's not so easy. So the classic problem that shows the power of this is the 8 queens problem, where you position these 8 queens on a chessboard so that none of them attacks each other. If you're familiar with the rules of chess, you'll know that a queen can attack horizontally, vertically, and diagonally. So this one here is actually a solution to this problem. All of them, are so that they don't attack each other. And so we're going to do this by backtracking. So backtracking means we start with a partial solution. And so we'll put a queen on the first row. We know there must be a queen on every row, because there can't be 2 queens on one row, or they would attack each other. And if you have 8 queens in 8 rows, that means there has to be exactly 1 queen on every row. So we'll put a queen on the first row. There's 8 possibilities. We'll put a queen on the second row. There's 8 possibilities for that. And then we throw out the ones that didn't work. We just don't pursue those any further. We do this with the third row, and so on. And so in each step, we're solving, the problem that we're solving is extend the previous solution one step further. So this is the thing that one of you asked about the quiz question. And so the quiz question was, it's the same question as this clicker question. So let's actually do this. It'll only take a minute. Where the heck am I? So let's do this quickly. Just give me your best guess. You've had it as a quiz question. Just tell me what you'd put on the quiz. So here's the figure. Blow it up. All right, if there's a solution, it clearly has to have 4 queens in it, right? So it's a 4 queens problem. So we only have to look at the ones here on the bottom. Oops. Now, the first one here, these 2 queens are going to kill each other, so that's not a solution. Here, these 2 are above each other, so that's bad. Here, these 2 are diagonal again, and these 2 are again above each other. So this figure actually has no solution to the 4 queens problem. The solution will appear later. I don't actually remember out of which one it comes. It might come out of this one here. I think you can put one here, right? Who's going to kill this one? That one should be okay, right? So, let's see what happened in our poll. And yes, so that was the majority answer. Someone asked a question about this, like somewhere there. Whoever asked the question, did I answer it? What's that? So we're okay with that question? Oh, you left? Oh, whatever. That is nothing I can do about that. Oh, since I have it here, we're going to have homework due the day before the exam. So, you thought I'd just make you write the exam? You'll have to write the homework with your left hand and the exam with your right hand during the exam. No, there's no homework the day before the exam. So I will give you a study list for the exam, but I will not grade it. All right, moving right along. So, so let's have a look at the code here. Yes. I'm gonna. It's in Canvas, but I'll take it out. Yeah, I'll put a note out. So I will give you when I get around to it. I'll give you a list of things that you should prepare for the exam. Talking of preparing for the exam, there's two things that you need to do now. One is look at the list of things that you need to bring for the exam. And it contains such things as your laptop, paper, a pen, an extension cord. Does everyone know what an extension cord is? It's surprising to me how many people show up on the day of the exam and say, an extension cord? What's an extension cord? And I have to explain it to them. An extension cord is one of those things that you can twist around your neck and hang yourself on if you're dissatisfied with your performance. So as you notice in this room, there are about 4 power outlets. And so in an exam, it's perfectly possible for people's laptops to run very hot and to go empty sooner. And what we will then have to do is we will have to take everyone's extension cords and hook them together and reserve the rest so that we can tie up the fire marshal if he or she were to look inside the room. So bring an extension cord, every one of you, okay? Bring a USB stick. Why a USB stick? What if the internet is down right at the crucial moment that we need to submit the work, right? So hopefully we won't need it, but bring the USB stick. So read through all of that and bring all of that stuff. The other thing you need to do on Monday, before Monday, is download. We're going to do a practice exam on Monday for 60 minutes, and then we'll talk about it afterwards for a few minutes. So I want you to see what these exams are like. So bring your laptop, and before you get into the classroom, download from Canvas there's a program that you need to decrypt the exam and then the actual exam. I'm giving you a test file that you can practice the decryption before that, but you want to make sure that you can do all of that stuff so that when the actual exam comes, that you know exactly what to do. So do those 2 things. All right, back to the queens. So we have a partial solution, and notice that partial solution, oops. Here we go. That partial solution has a method extend that gives us more partial solutions. Yes? That encrypted file contains the text of the exam. There's 2 that you're going to see right now. One is called test, and the other one's called practice exam. And the test one has the password swordfish. The practice exam I can't tell you the password. But when you hand me a $20 bill on Monday, I will. No, I'll give out the password on Monday for that. Right. And so that's how it's going to be working. I'll be putting the exam up, the real exam, on Tuesday night or so, that on Wednesday morning, you can download it. And that way, the reason I'm doing that is just in case internet doesn't work on Wednesday, or your internet doesn't work on Wednesday or something. That way we can be sure everyone has the exam. You may have seen, if you've taken 46A here, I believe Professor O'Brien does the same thing, right? Did she do the same thing? I mean, it's a sensible thing to do. So interestingly, you actually get the source code for the decryption program, so you could try to break it. Okay, back to the partial solution here. So extend gives us more partial solutions that are hopefully closer to where we are. There's examine, that examines whether two queens attack each other, and the way it works is that this one here loops through all the queens, this one loops through all the queens above it. Can I have a little less noise, please? Hey! And if one of the queens attacks the other, we abandon this whole thing. If we find that we actually have no attacking queens and we have the correct number, then we accept. Otherwise, we continue. Here's the extending thing. The only tedium about the extending thing is that you need to copy these partial solutions and make them look, and add a new queen in each possible position. So, and here we have the last and remaining clicker question, where you get to modify the program from the textbook, and you're supposed to make two modifications. One is it's supposed to be the 6 queens puzzle, not the 8 queens puzzle, and in this case, the queens don't attack themselves diagonally. They only can attack horizontally or vertically. So go ahead, click on code check, and modify away. You don't have to change the names to 6 queens. Leave it at 8 queens. But figure out how to get it so that it's 6 queens. Figure out where you need to make a modification so that the diagonal attacks don't count. And then send it off and tell me how many solutions did you find. Oh, and also give me a count of the solutions and not the actual solutions. So those are the 3 modifications. 6 queens, no diagonals, and count instead of actual solutions. So code away. Oh, wow. $32. All right, so time is running out. So I have here that 45 people got 4,320. But that's not right. Where does the 4,320 come from? I think that's because it's 8 solutions. No, that's 8 queens. Double check that and see if you get the right answer when you reduce it to 6 queens. 92 was the answer from the original problem, right? If you did nothing, you would get 92. If you kept the diagonals and if you kept 8. So the right answer is actually 720. And so I've coded it up as I was waiting for you, so you could check it out on the movie if you have trouble with it. So follow the movie to see how to do that. So again, in general, what it shows is that it's a really good idea to glance at the book code before the lecture, so that when you need to modify it during the lecture, that you know the lay of the land. All right, I'll see you Monday for the practice exam.